Next.
That's it.
Alright. Okay, so you can see there, they give you the amplitude, they give you the time here on the x-axis. They show you distance d is 125 meters. Where's distance d? That is distance d. What is given by d? D gives you 1, 2.5 wavelengths. Okay, so some way you must write 2.5 waves gives you 125 meters. What can you do with that information? No, I'm not going to say. Genevieve. You can find out? The wavelength speed. You're giving me two things there. Wavelength and speed.
Well, okay, the waves speed.
Okay, before you get to that, you can get the wavelength. Because is 125 meters for one wave? No. That is for 2.5 waves. Okay, so to get the wavelength for one wave, what are you going to do, Carabello? Okay, and that gives you what? $50 meters. Okay, then they give you more information. You can see there that for one wave, and I'm going to highlight that now, for one wave, it is 8 seconds. So, Karabu, what do they give us there? For one wave, it is 8 seconds. The? No, this is wavelength. This is wavelength. Length is meters. I'm telling you, one wave is 8 seconds. What is measured in seconds? No, speed is meters per second. They give us the time. The more formal word is the period. Capital T, the period. The time taken from one wave is 8 seconds. Okay, so can you see what I did? I haven't even read one question. I've looked at the information given to me and I've made a few assumptions regarding that. Okay. Right, what else do they give me here? You can see there's my rest position, my equilibrium position. And then the highest point, the crest, is at 75 and the trough is at minus 75. Lesego, what do they give us there? If they give us from the rest position to the crest is 75 meters. The amplitude. The amplitude is 75 meters. Okay, now that I've dissected, taken apart, analyzed my graph, now I'm going to read the question. The first question is, write down define the amplitude of a wave. So if they ask define, they ask give the definition for. Okay, Telefu, what is the definition for amplitude? Disturbance from rest or equilibrium position. Okay, you can see it counts 2 marks, so it's 2 or 0. Says where? Write down the amplitude of the wave.
It's 0 to 75 or 0 to -75.
Okay, so the reason why we said yesterday, I think it was D to A or whatever, is because we didn't know the value. But now that we have a value, you're not going to say from 0 to 75. You are just going to say 75 meters. Okay, you don't have to say 0 to 75. Next, it says calculate the frequency of the wave. Now, whenever something counts 3 marks, 3 marks means formula, substitute your values, and answer. So whenever something comes 3 marks in science, it's formula, substitute, answer. Always. Okay. So we must now calculate the frequency. Amara, how are we going to calculate the frequency? Is? But you don't have V yet. The next question is calculate speed. So we do not have the speed yet. So we can't use that formula. Different formula. Go back 1 page more. At the bottom of that page. The total time. Okay, so let's check. Do I have the total number of waves? I have 2.5 waves. Do I have the total time? Well, this is from there to there, it's 4. So from there to there, it's also 4, it's 20. That there gives me 20. So the total waves is 2.5. The total time is 20 seconds. And that gives you what, really? 0.125 hertz. But you could have also written it another way, or you could have said, I've just gotten for 1 wave is 8 seconds. So you could have also said, okay, for 1 wave it's 8 seconds, and you would have gotten exactly the same answer. If you wrote down 0.13, that's also fine. Okay, then at question 1.4, they ask calculate the speed of the wave. The speed of the wave. So there we have 2 formulas. You either have this formula or you have this formula. Now you could have used any one. Okay, sometimes one is easier than the other one. Sometimes you only have information to use one of them, but this time you could have used any one. Which one did you use to me? The second one. Okay, so the frequency, we just calculated that to be 0.125, and the wavelength is? 8. Wavelength 8. 8 is seconds, time in seconds. Now that is how many waves there are, but that's not the wavelength. 50 meters. Wavelength meters. Wavelength cannot be seconds. Okay, so 50 meters. And if you calculate that, Asina, what do you get? .25, and the unit? Meters per second. Okay, let's see if you use the other formula. Then the total distance would have been 125 meters. 125. And the total time is 20 seconds. 20 seconds, and if you calculate that, you also get 6.25 meters per second. So you could have used any one of the two, get the same answer. Okay, now grade 10s. In science, let's say you have made a mistake. Let's say here. Okay, for some reason you didn't write 2.5 divided by 20. You wrote 2.5 divided by 16. Okay? Then this would be wrong and your answer would be wrong. Okay? But now, so in a question from there to there, we do not work with your mistake. If you make a mistake with your mathematics, sorry, all wrong. Okay? In mathematics, you get marks for in a question. But let's say now you got your answer to be 0.3. And now you use that 0.3. Where did I write it down? There. Okay, because you have to use that answer F in this formula. So you incorrectly use 0.3 or you correctly use 0.3 there. Then we work with your mistake. Okay, so if you wrote down in here 0.3 and you multiply that with one another and you get 6, then you can get all 3 your marks. Okay, so in science, in a question, we do not work with your mistake. But from one question to the next, we do work. You'll see I write MF for met fout with your mistake. Then you can still get full marks. All right. Then question 1.5. It says there, the period of the wave is now halved. So we have two informations. The period is halved. And then they say the amplitude is doubled. The amplitude is doubled. Draw one wave pattern for the new wave. Indicate all the values. And you see it comes 3 marks. They'll also ask 3 things of you. They'll ask, draw one wave. The period must be changed and the amplitude must be changed. So those 3 marks, I'm looking for those 3 things. Okay. So there is my axis. I can see there the wave starts there at the top. So I'm going to draw one wave for them from there to there. For that you get 1 mark. Then they said the amplitude must be doubled. So Umulemu, they say the amplitude must be doubled. How do I indicate that here? So there I'm going to write 150. So for that you get a 2nd mark. You can also write here at the bottom is negative 50, 150. And then the last mark is for the period is halved. Where am I with my question? Doubling. The period is halved. What does that mean? What is a period? Okay, the time taken for one complete wave. So for one complete wave, it was 8 seconds. What is it going to be here? 4 seconds. 4. And that's your 3rd mark. Sharp? Okay. Right, then we're going to go on to our next type of wave. So we have done transverse wave. Now transverse wave was where the particles move up and down and the wave moves left and right. Now the longitudinal waves is where the wave moves left and right and the particles move left and right. Okay, so if you look at, say you look at this orange particle here, you can see it actually moves to the left and to the right. Yes? Okay, so that is a longitudinal wave. So there is the next definition. Longitudinal wave is a wave in which the particles of the medium vibrate parallel to the direction of motion of the wave. So they move in the same direction. Wave moves left and right, particles move left and right. Okay, then I tell you there, the medium's particles vibrate forward and backwards from rest position. So they vibrate forward and backwards from rest position, and they form a series of compressions and rarefactions. Compressions and rarefactions. Okay, so if you look here, there's the slinky. You can see here where they are pressed together, close together, it's called a compression. And there where they are far apart is called a rarefaction. Okay. Then a wavelength is from one compression to the next. That is the wavelength. Okay. So what is a compression? Here's the definition. Compression is a region, an area. So instead of region, you can say an area of high pressure in a longitudinal wave. And a rarefaction is an area of low pressure. Pressure is just how close are the particles together. So in everyday language, you'll say compression is where they are tightly packed. And rarefaction is where they are far from one another. Okay, but this is just formal language. Right, so here I wanted to show you the difference between a longitudinal wave and a transverse wave. Longitudinal, you can see the wave and the particle movement are parallel to one another, and here they are perpendicular to one another. Okay, so transverse wave goes up and down like this, and a longitudinal wave goes like that. Sure? Okay. Now, the problem is, it's very difficult to get information from a longitudinal wave. Like if you look at that, how will you get the amplitude? How will you get the period? How will you get the wavelength? It's quite difficult, because are you going to measure the wavelength from this one to this one? Like it's difficult to get the particles, so it's not that easy. So what we do is we have a machine that convert a longitudinal wave into a transverse wave. It's called an oscilloscope. An oscilloscope. So it changes this thing to this thing. So you'll see in an exam, they'll say, here is information regarding a longitudinal wave, and then you get this wave. Then it just meant it was a longitudinal wave, but it was put through this oscilloscope so that we can easily read it as a transverse wave. Okay, sharp? All right, but we go on with longitudinal waves. Now, one example of a longitudinal wave is sound. Sound waves are examples of longitudinal waves. So transverse waves was water waves, or like gamma rays or X-rays or light or something like that was transverse waves. Sound is example of a longitudinal wave. Okay, how does it start, a longitudinal wave? It is generated, it started with vibration. So my sound cords or vocal cords vibrate, and then it gives off sound. It cannot move through a vacuum. A vacuum is where there's no air particles. Vacuum is an empty space. There's no particles there. Okay, so if there's no particles, if there's no nothing, then sound cannot travel there. And that's what I said. If you are in space and you try to scream, you won't even hear yourself, because there's no particles to transfer the energy. It can only move through material medium, meaning gases, liquids, solids. Right, now, if someone comes up the steps and they walk now on this pathway outside, if we are sitting like this, we will only hear them, notice them, when they come from a Stieberachens class. Maybe halfway here. We will hear their footsteps on the ground. But if you lie on your arms and you put your ear on the desk, when will you start to hear them? Almost at the beginning, at the stairs, you'll hear something's vibrating, something's happening. Okay, why is that? If you remember from grade 8, you did the particle theory in grade 8, where you said solids vibrate on a place, yes? Liquids glide over each other, and gas particles move like this all over the place. So, now, when I speak, the sound moves through air. Air particles are far away from each other, so they take a long while to collide with one another to get the sound to transfer to next. But if someone is walking and makes a sound through the ground, then because it's on a ground that is a solid, the particles are closely packed, so they collide much faster with one another, so the sound travels faster. Have you experienced that before? Have you put your ear on the... Yes? No? Let's do that experiment. Let's sleep in. Quickly go to the end of the outside.
Outside.
Outside. Now when you run, you must run not light, you must stand. Now don't fall asleep. Okay, so your ear must be on the table. You hear? Is he too light? Are you tired? Alright, Chuck, thank you. Alright, so you've been hearing what from the start when you started? When? Somewhere. But if you was just running and you were abstract, you would not hear it all the way from here. You would start hearing somewhere here where the windows are open. Alright, so when something, or when sound travels through air, through gas, it takes a while. Why? Because the particles are far apart. When they travel through a solid, particles are closer, so they collide faster. Alright, so it says here, it's faster through liquids and the fastest through a solid. Okay, then how does sound travel? There's pulses, the rarefactions and the compressions, and then it gets to your ear, and then your ear translated into hearing. Then the human ear can hear sound with a frequency between 20 and 20,000 hertz. Okay, so this is important for you to know this value. Your ear can hear from 20 to 20,000 hertz. So if something is above 20,000 hertz, we call it ultrasound. Then you can't hear anymore. Dogs and cats and animals, they can actually hear that, but you can't. Your ear can't hear that. And then I've spoken about an oscilloscope changes sound waves into transverse waves. So it changes longitudinal waves into transverse waves so that you can see the pitch and the amplitude and. Ma'am, what is pitch? We haven't spoken about pitch. Pitch is frequency. Did someone go to the choir auditions yesterday? Hoekom nie? There's no one singing the choir in church. You don't go to church? Why? It just means that you can sing. And if you enjoy singing, you enjoy singing. Alright, so pitch is another word for frequency. And we're going to speak about pitch a bit later. Alright, then speed of sound. Speed of sound. The speed of sound in air at 20 degrees Celsius in normal air is 343 meters per second. Okay, another way of saying that, so that's the speed of sound, is it takes 3 seconds to move 1,000 meters or 1 kilometer. Okay, so if there's thunder and lightning, if you see lightning, right, then you can start counting 1, 2, 3, 4, 5, 6. For every 3 seconds that you count before you hear the sound, it's 1 kilometer away from you. So if you see the lightning and you hear and you count 1, 2, 3, and then you hear the sound, then you know that lightning strike was 1 kilometer away from where you are standing. Okay, so that's another way of thinking about it. So it moves 1,000 meters or 1 kilometer in 3 seconds. Then it says, when an aircraft approaches the sound barrier, the sound waves are compressed. This compressed energy explodes when the aircraft passes through the sound barrier. In other words, it flies faster than the speed of sound. So it just means when you have I know that looks like a fish, but it's an airplane. If that airplane flies, it gives off sound waves, right? You'll hear the airplanes, yes? Now, sometimes the airplane flies faster than 343 meters per second. Then the waves that it gives off are compressed. So there's the airplane moving and it's compressing all the sound waves together. And there where the sound waves are all together and the airplane breaks through them, that is called a sonic boom. That's why you'll hear like and there goes the airplane. Have you seen that in movies? Okay, so we call that a sonic boom. So it moves faster than the speed of sound. Right, you can see I didn't highlight anything there, just for interest sake. Then the speed of sound varies according to the material it is in. At air, it is at 0 degrees Celsius, when it's very cold, is 330 meters per second. And when it is warmer, 30 degrees Celsius, it's at 350 meters per second. Why is that? Why is it that when it gets warmer, the speed is faster? Where are we with our questions? Did I start? Yes, I did start, and we are back with Genevieve.
So the particles in the air basically get heated up and they have more energy, so they vibrate faster.
Prachtig. So it's like you guys, when it's very cold, what do? You guys just sit like close to one another and you vibrate and you don't move around. And when it's warmer, you are more free to move around. Except when it's really warm, then we all just die down here. Okay? But when it's cold, the particles do not have enough kinetic energy. So they move very slow, so it takes a while for them to glide to transfer energy. But when it is warmer, they have more kinetic energy, movement energy, so they can fly faster and air travels faster. Right. Then in water, speed of sound is at 1,400 meters per second. 1.4 kilometers per second. That's how fast it travels. That's very fast. And then in steel, it is 5,000 meters per second. So 5 kilometers per second. That's very fast. Okay? And then just for interest sake for now, the speed of light waves is 300 million meters per second. So that is why you first see the lightning and then you hear the lightning. Because you see the light travels a lot faster than what the sound is traveling at. Okay. Right. Then sometimes we work in very big units and we must convert. So 1,000 hertz is the same as saying 1 kilohertz. Karabelu, what is 1,000,000 hertz or 1,000 kilohertz? That first packet, when you go kilo and then the next one is? Yes, it's 1 megahertz. And then 1,000 bigger, Karabu? 1 gigahertz. Okay. Right, now we're going to do some calculations regarding sound. Okay, you can see there, it's exactly the same formulas that we just had. Alright, with all of the different symbols. Let's read the question. It says, a guitar string vibrates at 512 hertz. That means, that's the frequency. It vibrates, it makes 512 waves up and down per second. Okay, that's very fast. If the speed of sound is 43 meters per second, calculate the wavelength of the sound motion. Okay, let's say we're going to start with an info table. They speak about 512 hertz. What information do they give us there? And what's the symbol for frequency? F. Alright. Then Telefu, they give us 343 meters per second. What information do they give us there? What symbol goes there? Look here. What symbol goes with 343 meters per second? Velocity. See where? They say calculate the wavelength. What is the symbol for wavelength? Yeah. Yes, and what do we call that one? Sounds like a sheep, a small sheep. Lambda. All right, Amora, give me a formula that I'm going to use to solve that problem. The third one, this one. Did they give us time? Did they speak about the period? Did they ask the period? Can you see these symbols coincide with these symbols? Yes. Okay, so V is F times lambda. Now you always write down a formula exactly like it is given on the data sheet. Then you substitute your values. And then only do you rearrange. Okay, really? I want lambda. So what am I going to do with that 512? You are going to divide. Divide. Yes. Okay, and then you have lambda is equal to what to me? 0.6. And the unit? What does the M stand for? The meters, yes. Right, next question they ask. Does sound travel faster or slower in hot air compared to cold air? So Asina, in hot air, does sound travel faster or slower? Why? Yes, so you're going to say in hot air, particles have more kinetic energy, thus they collide faster and propagate energy faster. What does the word propagate mean again? Release, transfer, give off, share, blah, 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 blah. Alright, so grade, thanks. I'm going to stop there for today. I want to give you your homework in that book. So while you are starting your homework, I'm going to come check your books. In this book, please go to page, I think it's page 20 of the science book. Page 20, yes, that's activity 4.2. You are going to do number 1 and number 3. Number 1 and number 3. Sharp. So you can start with that now. When I come to you, I'm going to just check your writing out and your homework.